the important lesson we learned from the Tohoku earthquake is we need real-time observation of ground shaking. So we want to predict ground shaking, so we need to real-time observation of ground shaking. So second is the feedback of the real-time observation into prediction. We compare the prediction and real-time observation, and we improve our prediction model if necessary. So third is the repeated application of the feedback. Repeated application of the feedback. We realize this process is very important for actual operation of earthquake early warning. So I believe this is much more important than the source parameters such as hypopotential location, moment magnitude, rupture extent. And we will realize this process by introducing data assimilation, real-time shake map, and simulation of wave propagation. First, let's review the Tohoku earthquake. As Nakamura explained, JMA-EW was issued for Tohoku regions as rapidly as possible, as rapidly as the system was designed. So, but it's not perfect. So the performance fell short in this respect. First is the under prediction Kanto region. Seismic intensity 4 was predicted for Kanto regions, but actually seismic intensity 6 was observed. This is due to the large extent of the source rupture. Second, false alarm for aftershocks. That is, warning was issued, but shake was too weak. What happened? Okay, aftershock activity is quite active. So multiple aftershock occurred simultaneously. In this case, system confused, and the system misinterprets them to be a large single event, which leads to overestimation of magnitude, which leads to false alarm. So addressing this problem has become our important project last 3 years. And 3 years ago, we started following fundamental questions. Hypopotential magnitude. Are they the only one approach for earthquake early warning? Moment magnitude at source extent, the only one method for precise EW. We started this fundamental but important question. Our answer, no. We have a different approach, another method, and different tactics. For example, looking at the wave propagation from several seconds before and present, and then we predict situation of several seconds later, 10 seconds later, or 20 seconds later. I will show an example. This is a magnitude 7.4 earthquake of 2 years ago. So let's predict ground shaking at Tokyo. So now, looking at this animation, it's now arrived, now it's shaking. Okay, now you predict ground shaking successfully, but you didn't care much about hypopotential, much less magnitude. Anyway, yellow or red approaching to you or not, that is important information. So based on this sense, we will construct our prediction method. So here, I would like to clarify, for earthquake early warning, subject is a prediction of ground shaking, not rapid determination of hypopotential magnitude. Hypopotential magnitude is a method to go to prediction of ground shaking. So magnitude, hypopotential magnitude are not necessarily required. The importance is the prediction of ground shaking. I'd like to clarify here. So including current JMA method, many network methods based on the following idea, that is, from observation of shaking, hypopotential magnitude are determined, and then prediction of shaking is performed. That is a two-step approach. Okay, this is something similar in baseball play. In a baseball, batter hits the ball and fielder try to catch it. Okay? So in this method, this information and when balls here, these information are used for the interpretation, velocity and direction when batter hits the ball. And using this information, this guy predicts the point the ball is falling, and he tries to catch it without watching the ball. I don't think he's a good player. Okay? Many players play something like that. Once this information is obtained, this information is not so important. So balls here, this information is much more important than the velocity and direction when batter hits the ball. So our case, from observation of shaking, directly prediction of shaking, time evolutionary prediction. So for time evolutionary prediction, two processes are required. First, how to estimate the present situation precisely, that is real-time estimation of distribution. Second, how to predict future time evolutionary from the present situation. From the viewpoint of the solving the differential equation, first item corresponds to estimation initial condition. Estimation of initial condition. Second is the calculation of wave propagation. So estimation of the present situation and then prediction of future time evolution. We experience these two processes in everyday weather forecast. Okay? Especially on the numerical weather forecast, numerical weather prediction, present situation, that is pressure, temperature, wind speed, wind strength, input into supercomputer. And then based on the physical process for atmosphere, physics of thermodynamics, we predict the situation tomorrow or the day after tomorrow. Based on the similar idea, we will carry out numerical shake prediction. That is strength of shaking, propagation direction are input into physics of wave propagations. And based on the physics of wave propagation, we predict the situation 10 seconds later or 20 seconds later. Okay. For now, how estimate the present situation precisely? For this estimation, the most important is, of course, is observation, enhancement observation. And we will apply correction of site application factor in real time, and also we use data assimilation technique. On the second, prediction of future. This is a physics of wave propagation. So finite difference method or a boundary integral equation method are well known. They are exact one, but it requires much computation time. And we have a radiative transfer theory. This is a high frequency approximation, but less computation time. So in the presentation, I will explain a little bit about data assimilation technique, and also I will show an example using this radiative transfer theory. So first, data assimilation. Data assimilation is a technique to that is estimation of present situation precisely. Now we want to estimate distribution precisely. But unfortunately, we don't have so much quite dense observation network. We don't have 1 kilometer mesh network. Our observation is something like that. This indicates the location, KickNet and JMA network. So from this few data, how to estimate this station precisely? This is our current problem. The simplest way is just to draw the contour. Just to draw the contour. This is the simplest way. And we are a geophysicist who know the physics of wave propagation. So one time step before this situation is given. From this situation, we can anticipate present situation. Anticipation from one time step before and actual observation combined, and then estimate present situation. This is the basic idea of the data assimilation. So present observation in this way, and one time step before observation in this way, and two time step before observation in this way. So using all past data, present situation is estimated. Okay. So focusing on these three, this is a repeated application of physics of wave propagation. That is simulation of wave propagation. In the simulation of wave propagation, actual data is included. Actual data is assimilated, and simulation of wave propagation is carried out. So now using a data assimilation from past to present, all past data is used, and then current situation, current distribution is estimated as precisely as possible. Next step is the future, prediction of future. So future, we don't have observation, of course. So physics of wave propagation repeatedly apply. That is, from this initial condition, simulation of wave propagation is performed. Okay, so this is the example of estimated wave field using data assimilation technique. From this initial condition, we predict 10-second later situation or the 20-second later situation using the physics of wave propagation. In this case, radiative transfer theory. This is as it was so-called wave field, true wave field. For example, this distribution is estimated something like that using a data assimilation technique. And from this initial condition, we predicted the 10-second later situation and 20-second later situation. So compare this one and this one, and this one and this one. This comparison indicates how precise the prediction is. Okay, so someone said, okay, here, no prediction. Why? So, okay, this earthquake has not occurred yet. This earthquake occurred 4 seconds later in future. So it is impossible to estimate distribution of future earthquake. This is not a problem of ASCII RE1. This is a problem of ASCII prediction. Okay? So I will show an example. So this is a simple event case. Okay? Oh. This is a single event case. Okay, so it looks good, but it's the simplest case. So what about more complicated case for multiple simultaneous earthquake? Or this is a case of the multiple simultaneous earthquake. Okay, something like that. So it looks good, but there are synthesized data. So what about actually observed data? So I bring that data from Tohoku earthquake. But actually, this actual application of this method to actual data, we need one more process. That is a collection of site amplification, factor. So now, collection of site amplification factors, Hoshiba 2013 BSSA and Aoki and Hoshiba AGE or Hayashimoto et al. Poster session there. For detail, refer these papers. So here, site condition. Site condition is virtually replaced with that of Otemachi Tokyo. Difference of site factor is removed. All site has a common site effect that is same as Otemachi Tokyo. From this input applied data assimilation, we obtain a real-time shake map, and then we predict 10-second later situation, 20-second later situation. So I will show this example. Okay. Oh, wait a minute. So let's predict Tokyo. Oh, now Sendai. Strong shaking at Sendai, but probably not so much influence of Tokyo. Well, Sendai again strong ground shaking, but not so much influence again at Tokyo. Here, strong ground motion appear, and then it's approaching to Tokyo. 20 seconds before, 10 seconds before, it's now arrived. It's now shaking. Probably it's gone. Okay, something like that. I repeat again. So first strong shaking from first SMGA, okay? And second strong shaking from second SMGA. And third, fourth, fifth SMGA combined and then approaching to Tokyo. So SMGA which shakes Sendai and SMGA which shakes Tokyo are definitely different. Okay, I'll show this animation one slide before. And this is the actual observation of seismic intensity at Otemachi, Tokyo on JMA scale. So blue is the 20-second ahead prediction, this one. And red is the 10-second ahead prediction, this one. And 5-second ahead prediction is green. And here, for example, lapse time 130 seconds, strong ground shaking is observed around here. And then we predict about 20 seconds later, this strong ground shaking will arrive at Tokyo. And actually, 20 seconds later, that is lapse time 150 seconds, strong ground shaking was observed around Tokyo. But 20-second ahead prediction and 130 is a little bit over-predicted compared with the actual observation of 150 seconds. I mean this difference. So this over-prediction is improved, decreasing with real time, 10 seconds and 5 seconds ahead. Usually, distant future is less precision, and near future is good precision. Okay, so around here, we observe the strong ground shaking propagating in this direction. So let's track this strong ground shaking. So next slide. The next slide is around here. This is a real-time shake map. And this is a 10-second ahead prediction and a 20-second ahead prediction. So let's predict the shaking at Kofu. Okay. Kofu, well, moderate shaking is approaching, now it's arrived. Well, it will continue this level of shaking. Where strong shaking appear, it's approaching, it's now, it arrived now shaking, it's gone. Probably Nagoya, it will start soon. Okay, so our prediction is something like that. So in this method, site collection is very important. Here, this is a with site collection. This is the same as one slide before. This is a without site collection. So okay, so comparison this one and this one indicate how important site collection is. So please compare the two animations. Okay. Okay, which is smooth propagation. Moderate shaking is propagating, and strong shaking is propagating. And here's, as you imagine, and here's a mountain region. At mountain region means a hard rock site, so it looks disappear. And here is a basin structure. Basin structure, it continues strong shaking. Okay, I will show one more example. This is a 2004 Mid-New England earthquake, magnitude 6.7. After this main shock, quite active aftershock followed. Well, it's heavy. Go. It's go. So magnitude 6.7 earthquake occurred and strong ground shaking approaching to Tokyo. But compared to this direction, strong shaking is propagating this direction. Okay. And focusing on the focal regions, small aftershock occurred repeatedly, one after another. I show about 5 minutes, but aftershocks occurred repeatedly. So small aftershock. And then magnitude 5.8 aftershock. Oh no, this one magnitude 5.8 earthquake. Okay, so this real-time prediction, it's much more precise than that of hypercentral magnitude. Because not only hypercentral magnitude, we can compare prediction observation, and then, if necessary, we revise our prediction model. That's feedback. Compared and feedback. Feedback of actual observation, applying data assimilation, which leads to more precise prediction than that of hypercentral magnitude. Okay, this is the final slide. Summary. Applying data assimilation, we introduce feedback of actual observation into prediction, which leads to more precise prediction for large extent and multiple events. So finally, we compare against source information method and real-time shake mapping method. So for the real-time prediction of ground shaking, which looks more useful, precise, robust. Okay, so I admit this is a method, and this is a powerful method. So summarizing my presentation will be represented by the one phrase, this phrase. Okay, real-time shake map enable us to predict future. Okay, thank you very much.
Time for maybe one quick question.
So is it much of a problem that there are waves like the ones that hit the MOHO and that you can't see at the surface and are hard to know what they'll look like when they come up?
When you mean a 3D structure.
Right.
Calculation is possible to in 3D, but when the data assimilation is limited on the surface, so that is our future problem to solve. Difference of the 3D case and the 2D assimilation. How to handle this difference? That's important point.